So hi everybody. Today we're going to be doing a lab on buoyancy, and just to remind you what buoyancy is all about, the buoyant force refers to this upward force that a fluid will exert on an object when that object is immersed in a fluid. So let me just give you a simple example. Let's say we have a log made out of wood, and we put that in some water. We know that it will float there, it won't just sink to the bottom, and the reason it floats there is because of the upward buoyant force being balanced out by gravity. So we also learned about Archimedes' principle in lecture, and Archimedes' principle gives you a very simple way of calculating what the buoyant force actually is. So here's how it goes. Archimedes' principle says that the upward buoyant force that a fluid exerts on an object is equal to the weight of the fluid that that object displaces by being in the fluid. Okay, so buoyant force is equal to the weight of displaced fluid. We can think about this in an equivalent way, because weight, of course, is just a force of gravity. We can think of the buoyant force as being the mass of displaced fluid times g, the acceleration due to gravity. Or equivalently, we can think about the buoyant force as being the density of displaced fluid times the volume of displaced fluid times g. These are all just different ways of saying the same thing, okay? But it boils down to the fact that the buoyant force is equal to the weight of the displaced fluid. All right? So we're going to be putting this idea, Archimedes' principle, to the test in today's lab and see if it holds up. So let me show you now what the experiment looks like. Now let's take a look at the experimental setup here. First thing I'll point out is that we have a force probe. Now the way that these force probes work is that they measure the force that's applied to the hook, either pulling out on the hook or pushing into the hook. So for our purposes, since we have the hook facing down, this is going to measure the vertical force applied to the hook. We can actually read out what that force is using our computer interface over here. And what's connected to the hook? What's creating a force on the hook? Well, we have a string, and that string is attached to this vertically hanging cylinder. This is a cylinder made out of some kind of metal. Now, directly below that, what we have is a metal cup which has a spout. Now, although you can't see it, this metal cup is filled with water to the point where it's just about to spill out of the spout. So it's filled to right about here, so that if we displace any of the water, it's going to start spilling out of the spout here. So here's what we're going to do. Right now, the object, this metal cylinder, is completely out of the water, so it's not displacing any of it, and we can measure what the force or this tension in the string is. Then what we'll do is we'll lower this entire apparatus down until the metal cylinder is completely in the water, and we'll do two things. First, we'll measure the force of tension here once again, but it's going to be different because now there is a buoyant force from the water acting on the cylinder. So that the fact that there's now a buoyant force when we lower this thing into the water changes the tension that we measure. That's one way we're going to assess what the buoyant force is. Also, when we put the cylinder in the water, as I said, it's going to displace some of the water, and that is going to go directly into this cup. So we can measure exactly how much water has been displaced by the cylinder. That's more or less how the experiment goes. That's how we're going to find out what the buoyant force is. All right, so the first measurement we're going to take is the mass of the beaker when there is no water in it. So later on what's going to happen, as I said, water is going to spill into this beaker, and then we're going to measure the combined mass of the water in the beaker. But all we care about is the mass of the water, so we're going to have to subtract off eventually the mass of this beaker, so we have to know what that is. So let's take a measurement of the mass using this triple beam scale. So it's obviously more than 100 grams, but less than 200. And let's fine tune it. So it's more than 140, but less than 150, so somewhere in between there. And then we'll fine-tune that even more. Alright, and it looks like now we've balanced the scale. And in order to do so, we have a mass of 148.7 grams. So 148.7 grams would be the mass of the beaker all by itself. Okay, next, we're going to make some more measurements. And the first one, we can just make the measurement immediately. We have the cylinder hanging from the hook of the force probe, and the cylinder is not in the water. So the force probe is currently reading 0.490 newtons. So that would be the force when the cylinder is not in the water, 0.490 newtons. Okay, so what happens next is we're going to lower this entire apparatus so that the cylinder is completely in the water. So I'll do this slowly. And notice how some water is beginning to spill out of the spout. And I'll just keep going until that entire cylinder is underwater like this. And we'll just let the water keep spilling out. But the first thing we can notice is that the force probe reading has changed. It's less than before because now there's a pretty substantial buoyant force pushing up on the cylinder. That's going to reduce the tension in the string. So what we're reading is, from the force probe, 0.322 newtons. So the force when the cylinder's in the water is 0.322 newtons. All right, next thing I'm going to do here, it might look like the water has finished spilling out of the spout, and I can just now put this on the scale and weigh it, but that's not quite right. See, water has a property called surface tension, which makes the water get stuck in the spout a little bit. So what I'm going to do is just sort of tap on that spout, maybe stick this pencil in there a little bit, and get all those excess water droplets out of the spout. Okay, and then once I'm confident that I've gotten all that water out of the spout, then we can go ahead and measure the beaker. Okay, so the next measurement we're going to take is the mass of the beaker with the water inside of it now. So we'll start by trying to fine-tune that mass with the triple beam balance. Okay, it looks like it's somewhere between 100 and 200 grams, so we'll fine-tune that some more. Okay, it looks like it's more than 160 but less than 170. So we'll fine-tune the last bit of that. Alright, and then it looks like we can get the scale to balance exactly at 167 grams. So the mass of the beaker with the water in it is 167 grams on the dot. Alright, so I've just shown you one complete trial of the experiment and all the data that comes with that. So what we're going to do is repeat for 2 more trials. So we have a total of 3 to average over when we do the analysis. I'm not going to show you that on video. I'm just going to flash the numbers for those other trials on the screen because, again, the procedure is exactly the same thing. So here are those numbers. So the last measurement that we need to take is the dimensions of the cylinder that was used throughout the experiment. We're going to measure those dimensions using vernier calipers, which are very accurate. These go down to the nearest 1/100th of a millimeter. So we'll start with a measurement of the diameter of our cylinder. And we're getting 20 millimeters right on the dot. So 20.00 millimeters for the diameter. For the height, let's see what we have. So the height of this is 56.64 millimeters, and there you go. All right, so that's it for this experiment. You've seen how it works. You have all the relevant data. So now you should be ready to do the analysis, which is explained in the worksheet that goes along with this video. So essentially what that's going to involve is calculating the buoyant force 3 different ways. The first way is like this. We have the data from the force probe. Okay, we have the force when the cylinder was in the water. We have the force when the cylinder is not in the water. Just by comparing those 2 values, we can directly calculate what the buoyant force was. Another way we can do it is by using the water that was displaced, that went out of the spout into the beaker. That's another way we can assess what the buoyant force is. And then lastly, we have the dimensions of the cylinder. So you can calculate the volume of the cylinder and calculate the buoyant force that way as well. So with these three different ways of assessing the buoyant force, you should find very close agreement. If you're not finding close agreement, check your calculations again because something went wrong. And that's really it for today. So I'll see you in the next lab video. Until then, be safe and be healthy out there. Take care.